In the first part of this video lecture, we have already seen the definition and many examples of measures, and now we're going to do some properties of measures that will complete the first section of this video lecture. We have seen that a measure is a non-negative function defined on all measurable sets of a measurable space, satisfying two properties. First, the measure of the empty set is 0. Second, the measure of a disjoint countable union of sets is the sum of the measures of these sets. We now move to the basic properties of measures. So let omega, f, and mu be any measure space, and we're going to prove that it has the following properties. The first one is called countable sub additivity. Sub additivity means if we take any countable family of sets in the sigma algebra F, so these are measurable sets, and we are not requiring them to be disjoint, then the measure of the union of these sets is bounded from above by the sum of the measure of these sets. This is known as the union bound. The second property is a very robust one, it always holds, is the property of continuity from below. What does it say? If we have a family, a countable family of elements of the sigma algebra, which is increasing, meaning each set in this sequence contains the previous set, then the measure of the union of all these sets, so they're increasing. When we take union, we're talking about what they become at infinity. The measure of this union, which we denote as the measure, this union we denote as the limit when n tends to infinity of an. So an increasing sequence, we say it has a limit, and the limit is the union. The measure of this set equals the limit as n tends to infinity of the measure of each set of each of these ans. Here the third property, which is not that robust because it has an assumption that has to be checked, and there are counterexamples in case the assumption is not satisfied, is continuity from above. So now instead of having a sequence an that is increasing, and as it increases we can take the union to be their limit, now we have a sequence of measurable events which are decreasing, meaning each set is contained in the previous one. And we need to assume that at some point the measure of these sets become finite. If it never becomes finite, this may be false. So what we define is the measure of the intersection of all these events that are decreasing, which we call the measure of the limit as n tends to infinity of an. We call a decreasing sequence of events. We refer to its limit as their intersection. This equals the limit as n tend to infinity of the measure of an. In some shorter notation, we can say that if an increasing sequence of events an, it increases to an event a or a set a as n tends to infinity, this implies that the measure of the ans increases to the measure of a. And likewise, if a decreasing sequence of events that in the limit gives a set a, and such that one of them, let's say the first of them, has a finite measure, then the measure of these sets an will decrease to the measure of the set A. So we start by proving continuity from below. Suppose an is an increasing sequence of measurable sets, that means sets in the sigma algebra. So since it's increasing, we can take its union, call that union A. So suppose an is a sequence, an increasing sequence of sets that increases to A. And we define another sequence of set as follows. We take B1 to be A1, and for each k, we take bk plus 1 to be ak plus 1 minus ak. So the point is that these bk's, they don't miss anything because everything new in ak plus 1, they got it, but they are disjoint. That's the nice property of these sets bk. Then, because they are disjoint and the union of the first k sets in this sequence of sets is exactly ak, then because a measure is additive and they are disjoint, then the measure mu of ak is given by the sum of the measure of the first k bj, so b1, b2, b3 up to bk. And likewise, because A is the union of all these bj's, all of them, the countably many bj's that we have defined here, and they are all disjoint, then we have that the measure of A is the sum of all these infinitely many measures of bj's. But now, just by definition of an infinite sum, we have that summing over the first k numbers and letting k tend to infinity, this converges to the sum, the infinite value of the infinite sum. And this concludes the proof because we have exactly proved that mu of ak converges to mu of a, which is what continuity from below states. Now, for continuity from above, we take some m such that mu of am is finite, and for each n larger than m, and this is a decreasing sequence of sets by assumption, so an is a subset of am, then by basic properties of measure of the property of the measure being additive, since am can be written as the disjoint union of an and the rest, am minus an, then we have that the measure of am equals the measure of an plus the measure of this complement here. And because this sequence of events here, now we're taking the complement of an with respect to am. Now this sequence of events of sets is increasing, and since it's increasing, we can use the previous property, which is continuity from below. So this one does converge to the measure of am minus a as n tends to infinity. And this is just a finite number, we just keep it there. So these are all finite numbers for every m, for this value of m at which the measures become finite, and every n after that. But now, this difference here, the difference between the measure mu of am and the measure mu of am minus a, well, these two are disjoint sets, these ones here, and their union is exactly equal to am, and therefore the measure of am equal the sum of these two measures, which means since this is finite, the measure of am minus this number equals the measure of a. And this concludes the proof. Why? Because we started with the measure mu of an, and we proved that it converges to the measure of a. So this concludes the proof of continuity from below, assuming that at some point these sets, they have finite measure. Now for sub-additivity, first we note that when we're talking about a finite union, this follows immediately from the properties of the measure mu being additive, and for a complete proof, we can do what we did in the proof of continuity from below. We just call this union here ak tilde, so now it's increasing in k, and we define b tilde like this, and this measure will be exactly equal to the sum over j equal 1 up to k of bj tilde. This is just the same argument as we used for the proof of continuity from below, but now there is a mu missing here, so this is equal because these are disjoint, and now these bj tilde, they are a subset of aj, so we can compare these two directly. So we have established finite subadditivity, but now we have to go to countable subadditivity. But for this, we can use continuity from below here. So this converges to the mu of the union j going from 1 to infinity of a j. And this sum that is stopped at k here, it will converge to the sum when j goes from 1 to infinity of mu of a j. So now if we take the limit, we get this on this side of the inequality and this on this side of the inequality, which also completes the proof.